Hi everyone, thank you for having me in SDC 2022. My name is Amir and today I will be presenting our work on building an object-based STaaS solution with Poseidon Storage. In our presentation, I will start with Poseidon OS introduction. We will then talk about storage as a service with object storage. We will describe the STaaS solution we have built with Kubernetes with Poseidon Storage, followed with a demo. Then we will see the performance benchmark numbers for our setup. Poseidon is an open source NVMe fabric solution developed by a joint collaboration between Samsung, Inspur and Never Cloud. It is targeted for cloud and hyperscale data centers. Poseidon hardware supports a composable architecture based upon the U.2, E1.S, E3.S SSD form factors for enabling storage disaggregation using NVMe fabric protocol. The Poseidon OS, also called as POS, is a lightweight storage OS that offers best performance and storage feature over a fabric network. Since Poseidon system is co-designed for both hardware and software, it commits to provide all the vital features of a NVMe fabric solution. My colleagues Badri and Arun in another presentation titled Poseidon OS, an innovative open source storage system and its exploration using Trident, will be describing the Poseidon OS in detail. I will talk about the Poseidon OS briefly here as our presentation is based on it. Poseidon OS, as you can see in this figure, runs as a user application on Linux kernel and it can provide volumes to the initiators via NVMe over Fabric, which are shown as virtual block devices in the initiator side. POS exploits the benefit of NVMe SSDs by optimizing the storage stack and leveraging the state-of-art high-speed interface. Also, it implements software-defined storage capabilities to meet the various needs of storage application in the data center. With POS, industries can easily build composable disaggregated infrastructure in their data centers. The latest version of POS is 0.11.0. It is available on GitHub. The Poseidon OS provides high performance volumes to initiators. Stable and consistent performance is experienced by the clients. It is a highly available system. It eliminates single point of failure for continuous operations. It has a robust interface for management and maintenance, for example, CLI commands and RESTful APIs. Today, cloud service providers or CSPs are constantly challenged with large volumes of data and increasing demand from customers for cost-effective storage. To solve these challenges, they provide software-defined STaaS or storage as a service, solutions for exposing the data as a service by abstracting the storage software from the storage hardware. STaaS services can be deployed with object, block, and file storage. CSPs are adopting object storage as their primary storage service for building their cloud storage infrastructure, as legacy storage systems based on file and block storage are limited in their ability to scale and struggle to manage high volumes of unstructured data. Object-based STaaS service is becoming popular as object storage is today the dominant class of storage for the cloud. Our goal is to build an object-based STaaS platform optimized for Poseidon storage. In our study, we found that most STaaS deployments available in the market are based on a monolithic architecture with no support for cloud features like multi-tenancy and orchestration. In monolithic systems, multi-tenancy is achieved by supporting multiple users and is not a true multi-tenancy. The storage nodes are partitioned for multiple users based on users, groups, roles, and policies. Orchestration and isolation of the storage is done by the storage layer itself. This architecture works well for a small scale deployment, but fails to scale as the number of tenants increases and is not as suitable for cloud. To truly become cloud scale, storage should be deployed with true multi-tenancy, and isolation and scaling of tenants should be done by cloud or orchestration platform like Kubernetes. as shown in the cloud scale deployment model in the figure. In this presentation, we will demonstrate how we have built an unique cloud scale object-based STaaS platform based on MinIO object storage. MinIO is an open source and supports both monolithic distributed deployments and cloud scale deployments. Let us see the object STaaS solution we have built on Kubernetes platform with Poseidon as backend storage. We are making use of MinIO operator, which is a Kubernetes plugin, to achieve multi-tenant STaaS solution. MinIO Kubernetes operator plugin enables and simplifies the deployment and management of MinIO object storage on Kubernetes. MinIO operator console provides the simple and intuitive web interface for creating the MinIO tenant. The diagram here presents the deployment of our multi-tenant object-based STaaS solution with MinIO object storage. The backend storage is configured on a Poseidon target. The Poseidon volumes are mapped to Kubernetes nodes and are presented as direct attached storage devices to Kubernetes with the help of MinIO Direct PV-CSI driver. Direct PV-CSI driver formats the pool of drives on all the worker nodes and makes them ready. A MinIO tenant essentially represents a MinIO object storage cluster. MinIO server pods are created in the Kubernetes cluster as the nodes of the MinIO tenant. Multiple tenants within the same Kubernetes cluster can be configured, for example, MinIO tenant 1 and MinIO tenant 2 in the diagram. Each tenant in turn can have different capacity, resources, and servers, as well as separate configuration like encryption and versions. This is true multi-tenancy architecture. Each tenant, while sharing the same physical infrastructure, is fully isolated from each other in their own namespace. They can scale independently. This design gives tenants the ability to protect themselves from any disruption on upgrade, update, or security incidents occurring in some other tenant. We have set up a private Docker repo to pull application images for running various workloads like data analytics, data ingestion, and AI/ML, and hosting them on MinIO tenant. To collect system metrics and back up the Kubernetes cluster, we have integrated Prometheus and Velero Kubernetes services with MinIO respectively. I am now going to show you how to create a MinIO tenant using a MinIO operator. This is our Kubernetes cluster. As we can see, there is one master node and 4 worker nodes. To start with, on the worker nodes, we connect and discover the NVMe volumes from the Poseidon target. The drives NVMe 1 and 1 to NVMe 1 and 8 are coming from Poseidon target. Now on the master node, the direct PV CSI driver will discover these Poseidon drives and mark them available. We can see the drives have been marked as available. We will now format this pool of drives using the direct PV CSI driver and move them to ready state to be consumed by Kubernetes cluster. We can see the drives have been moved to ready state. Once the drives are in ready state, now we will initialize the MinIO operator. We can see the MinIO operator pods are up and running in the Kubernetes cluster. On another master node terminal, we create a local proxy to the MinIO console to access the MinIO operator UI. Let us enter the copied token. To create a tenant, we hit on a create a tenant button. This will land us to a page where we need to enter the setup details of the tenant we want to create. We have updated these details. We have updated the name of the tenant, the Kubernetes namespace in which our tenant will reside. Please note that only one MinIO tenant per Kubernetes namespace is supported. We updated the storage class to Direct PV MinIO. This storage class is associated with the Direct PV CSI driver. The MinIO operator will generate the persistent volume claims or PVC against this storage class and therefore consuming the Poseidon storage. We have updated the number of servers to 4. So there will be 4 MinIO servers created in this tenant. Drives per server to 4. So the total drives in this tenant will be 16. Considering each drive to be of 2 TB capacity, the total size of the tenant will be 32 TB. We have updated the eraser code parity to EC4. Then we updated the resources like CPU request and the memory request for the MinIO server pods which has to be created. We can see the values on the right pan has been updated as per the values entered in these fields. Then we update the other sections like images, pod placement, identity provider, security, encryption, audit log, and monitoring. Please note that for audit log and monitoring, we have to update the storage class to DirectPV MinIO so that they are able to get the volumes from the Poseidon storage. Now we hit on the create button and wait for some time so that the required pods are created. This will generate the credentials which has to be saved for later use. Now we can see the MinIO tenant is up and running and the state has been set to initialized. Also the health is green. Let us go to the monitoring dashboard. We can see different metrics in this dashboard like uses, traffic, resources. This gives us interesting insights into the created tenant. Now on the master node terminal, we will see the pods corresponding to these tenants. We can see these pods have been created corresponding to our MinIO tenant. These are the MinIO server node pod which have been created, and this is the Prometheus pod for monitoring dashboard. Let us also check the service created for our MinIO tenant. So these are the MinIO services created which we will use to access the MinIO. In a similar way, we can create another tenant with altogether different sets of parameters using this create tenant button. The two or more created tenant will be truly independent of each other, and the beauty of it is we are able to achieve this using the same physical resources. With this, we have just completed the successful deployment of the STaaS with Poseidon Storage on Kubernetes. We did the performance benchmarking of the build Poseidon STaaS. We have used Warp tool to benchmark the STaaS. Warp is an open source tool for benchmarking the object storage performance. It is developed and maintained by MinIO. It has rich set of configurable options using which the test data and the workload can be tuned to be close to real world conditions. For example, it can be configured to run with different size of objects, number of parallel threads, enabling and disabling of TLS, etc. to represent the workload. For read performance, we run warp with get argument, and for write performance, we run warp with put argument. Testing of one or more MinIO hosts with one or more warp clients can be done in a coordinated and automated way by using warp distributed benchmarking. The diagram on left represents the warp distributed benchmarking. To run distributed warp benchmark, we need to create 4-node warp cluster. So each warp client node of warp cluster can generate traffic to all the nodes of MinIO cluster simultaneously. Each warp client instances coordinates with the warp server instance. Please note that all the clocks of warp client instances must be synchronized within 1 second of the warp server instance to start the distributed benchmark successfully. Moving to figure on the right, it captures the typical standalone MinIO STaaS setup used for benchmarking. We can see it has 4-node MinIO cluster with Poseidon volumes. All the four Poseidon NVMe-oF targets are connected to the MinIO node over 100 gig network interface. Additionally, we have 4-node Warp client cluster, again each client pumping the benchmark traffic on a 100 gig network interface. The MinIO cluster and the Warp cluster are connected to 100 gig network switch. Now let us do the math for the expected read and write numbers for the described setup. Since we have 4 MinIO nodes connected one to one with 4 Poseidon and NVMe-oF target at 100 gigabits per second network interface, that makes the maximum throughput achievable to be 400 gigabits per second for the MinIO cluster, which is equivalent to 15 gigabyte per second. Thus for read, it is 50 gigabyte per second, and for write, since it is configured with eraser code set to EC4, it is 25 gigabyte per second. Considering the overhead imposed by TCP and Ethernet technologies, we are expecting 80 to 90% efficiency. Therefore, we are expecting 40 to 45 gigabyte per second for read and 20 to 23 gigabyte per second for write. We ran benchmark with 4 standalone Warp clients on 4 standalone MinIO servers. The performance we achieved for a standalone MinIO cluster is 43 gigabytes per second for read and 23 gigabytes per second for write. The obtained throughput numbers are the base reference numbers. Now let us see the setup for Kubernetes MinIO tenant. As shown previously, we have Kubernetes cluster with 4 worker nodes and 1 master node. Each of the 4 worker nodes have Poseidon volumes. There is one-to-one mapping of the worker nodes and the Poseidon target. Again, the 4 worker nodes and the Poseidon target is connected over a 100 gig network interface. Also, all the Kubernetes nodes are communicating over 100 gig Ethernet interface connected to a 100 gig network switch. We can see in the diagram, 4 MinIO server pods are running in the MinIO tenant, and 4 Warp listener pods are created in the Kubernetes cluster for running the benchmark. Since the Kubernetes setup is similar to standalone setup with respect to network, applying the same math, we can expect to get similar or little lesser numbers considering the Kubernetes overhead. Basically, to start the Warp distributed benchmark in Kubernetes cluster, we need two YAML files, warp.yaml and warp-job.yaml. Both the example files are present in the Warp GitHub repo. First, we need the warp.yaml to create the Warp client listener pods. There will be 4 replicas of the listener pods and they will be listening on the port 7761. We create the Warp listener pods now. We can see 4 Warp listener pods are in running state. Now once the listener pods are up, we need to start the benchmark. For this we need the warp-job YAML file. Let us now check the warp-job.yaml file. We need to update the file with access credentials which was provided while we created the tenant. These are the arguments which will be passed to the Warp benchmark. We'll be using the get parameter to run the get workload which is equivalent of read. This is the name of the bucket which will be used for benchmarking. This points to the Warp pods which have been created. This option points to the MinIO server pods which have been created for the tenant, and we are accessing using this service created for the tenant. This signifies the number of concurrent operations which will be running, in our case 64. And finally, this is the object size which will be used for benchmarking and which is set to 512 MB. Now let's start the Warp benchmark. Now we have the pods for Warp job. To get the job logs, let's see. So we can see all the client traffic has started from the Warp nodes. The Warp benchmark has completed and the numbers we got for 512 object size is 23 GB per second for put operation and around 28 GB per second for get operation. The table on right captures the throughput numbers we observed with different object sizes. The number obtained is around 29 GB per second for read and 23 GB per second for write on Kubernetes cluster. As we can see for Kubernetes STaaS, the number for write operation are almost same as Monolithic STaaS, that is around 23 GB per second. For read, the Kubernetes numbers are lagging but are not at the extreme lower end. These are our initial findings. We are in discussion with MinIO to further fine-tune and improve these numbers. With this, our presentation comes to an end and we can conclude that in our presentation, we were able to build low-cost cloud-scale STaaS deployment on Poseidon using open source technologies. We successfully utilized the MinIO operator on Kubernetes to deploy the STaaS, which is cloud native. Moreover, in our deployment, we achieved comparable performance of Kubernetes STaaS as compared to standalone STaaS. Before we end, I would like to thank my co-author, all the attendees, and SDC India for providing us the platform to share our work.